Hi mathematicians, we are going to talk about the melting snowball problem. And so I think the problem, this is in section 3.9, it's related rates. And it goes something like this. You have a snowball. Let me turn on this light. What happens if I do that? Okay, so we have a snowball melting at a rate proportional to its surface area. Show that I think they write dr dt, or change in radius over change in time is constant. And they do tell you the formula for surface area. And they tell you that is 4 pi r squared. And that makes me feel good because we have a squared here and it's a surface area. And I always just like to take a little extra check on things like that. And so let's now look at the volume of the sphere. And they don't give you the volume of the sphere. I think I just looked that up, right? I don't have all of these things memorized, and if I don't use them a reasonable frequency, I forget too, right? So I looked that up also. So I haven't really done anything yet, but let's go back to the problem. So it has a snowball melting at a rate proportional to its surface area. A snowball is, there, let's make some complete sentences. A snowball is melting at a rate proportional to its surface area. What does that mean? In math, what does this sentence mean? At some point, you did a bunch of problems, or you should be doing a bunch of problems on Pearson, and they just keep telling you that things are proportional, things are proportional, things are proportional. And so what that means is that the dV, or the change in volume of the snowball over the change in time, equals K SA. I'm going to write SA. And what is SA? Where SA is surface area. Okay, how do you feel about that? Some of you might say, Beth, we're melting. This should be a negative K SA. That's okay too. Okay, it'll rectify itself, whether you use K or negative K. Each one is fine. All right, math has a way of working out. Okay, and so what are we supposed to do? We're supposed to show that dr dt is constant. Okay, and so you're like, I don't know, what? And that's how you feel a lot when you see a math problem sometimes. You're like, I don't see the end of this. I don't see where I'm going. Okay, well, let's just see where we are and see what we can do. So we have dV dt equals K SA. All right, let's go ahead and substitute in for this V. I'm going to go ahead and substitute in. So I'm going to take this V, and I'm going to take this V here, right? Because we're saying the change in volume over the change in time equals KSA. And the volume of my sphere is this. So I'm going to go ahead and rewrite D 4/3 pi r to the third dt equals K SA. All right, and so here I'm going to take the derivative of this, right, with respect to time. 4/3 is a constant, pi is a constant, and we're going to take the derivative of r with respect to time. Now, I don't necessarily have like an equation for r, right? And I know for implicit differentiation, they talk about how the equation is not explicitly written somewhere, therefore you use implicit differentiation. For me, a lot of times when I'm thinking about this, I feel like we need implicit differentiation because this r is changing too, right? So this becomes 4, well, I'm going to put the 3 up front. 3 times 4/3 times pi r squared times the change in r over the change in time, right? Acknowledging that as this snowball melts, the radius of this snowball is also changing, right? We have a large snowball, smaller, and then smaller. These changes are continuous, and the radius is getting smaller and smaller and changing along with the surface area and the volume. So to me, conceptually, sometimes this is when we're acknowledging that change. Equals K times the surface area. So let me just clean this up and see what we have. We have 4 pi r squared dr dt equals K. And now what I'm going to do is I'm going to substitute in orange here, use my orange crayon. For surface area, I'm going to come way up here. And I'm going to substitute that in here. Okay, and so as you can see, hopefully, these both cancel, and I get dr dt equals K, showing that dr dt, or change in radius over change in time, is constant.